So today I'm going to be talking some more about polymer-derived ceramics, but specifically about the role of free carbon and its impacts on the microstructure and some of the applications and the properties of polymer-derived ceramics. So first, I want to talk about some of the significance and why this is important. So PDCs can be very useful in a lot of different applications because of some of their desirable properties, such as having high strength and low weight, as well as having favorable electrical and thermal properties. And in situ carbon or free carbon is going to impact these properties. So learning more about free carbon is going to allow us to improve upon and tailor the properties of PDCs and allow for the development of better and improved applications of PDCs. So we saw this slide in my last presentation, but I just want to talk about it again. So PDCs have been studied for over 50 years now. And again, as you can see here in this graph, the interest and publications of PDCs has greatly increased over the last 10, 20 years. And this inset graph actually shows the number of publications of free carbon as well. So you can see that as the publications of PDCs have increased, so have the publications with regard to free carbon. So those are kind of interconnected, and it shows that free carbon is very important when you're going to talk about PDCs. And then again, of course, PDCs, we just kind of talked about on significance. They have a lot of interest in many different fields and applications. And then this slide again was also from my last presentation, but I just wanted to add it again to kind of talk a little bit about PDCs. So again, you're going to start with this polymer precursor, and then through heat treatment, you are going to turn it into a ceramic. And again, one of the main advantages is that these precursors can be shaped using polymer forming methods to create more detailed and kind of unique ceramics. Hi, Crystal.
Hello. So sorry, I'm late.
You're good.
We are recording, so
I was searching for the email for the link. I lost it.
all right, please continue, Mabel.
Okay.
We are recording, Crystal, so you can just, yeah.
Okay. So in situ carbon is often called free carbon or excess carbon because it is going to generally exist separately from the silicon or other molecules of the backbone of the ceramic or the polymer, and it's only bonded to other free carbon atoms. So as you can see in figure 4 here, all of that carbon is completely separate from the silicon backbone and the nitrogen, and it's only bonded to itself. And the free carbon is formed during and after the pyrolysis stage of the polymer to ceramic process. And the carbon atoms are found in the hydrocarbon groups in the polymer precursor, and then after pyrolysis, the hydrogen atoms are removed and only the carbon is left. So because it does exist within the PDC's microstructure, free carbon is going to play a role in determining some of the resultant properties, which I'll talk about in a few slides. And then as you can see here in figure 3, it's just kind of a different way of looking at it. The free carbon kind of forms like structures and kind of walls around that silicon portion of the ceramics. So this is kind of a general outline of the formation of free carbon within the polymer derived ceramics. So this first stage here, as you can see in this left corner, is the precipitation of free carbon. So this is going to occur at the first part of pyrolysis between about 600 and 800 degrees Celsius. And this is caused by the breakdown and the reorganization of the hydrocarbons. So that's kind of starting in this stage during the heating process. And then the second stage here is the nucleation or the forming of the basic structural units of free carbon. And so the carbon is beginning to form kind of a new phase. And this is occurring between 800 and 1000 degrees Celsius. So in this stage, the carbon layers are kind of beginning to stack to form these basic structural units. As you can see, this is an example of a basic structural unit. And also, as you can see in the image, there's still some hydrogen left, but the basic structural units are completely independent of each other. And then in the third stage here, this is going to be the growth of those carbon clusters. So the hydrogen is going to be removed, and these are going to form only carbon groups. You can see there's a lot more hydrogen here than in here, so those are being completely removed, and that's going to happen between 1000 and 1200 degrees Celsius. And then in the last stage here, oh, and also I forgot to mention that the basic structural units are beginning to link here, so they're not completely independent anymore. And then in this last stage, they're continuing to link, and this is going to be the graphitization of the existing carbon network. So the carbon stacks are going to rearrange and expand and form into a material that has a crystalline structure that is pretty similar to that of graphite. And this is going to happen at very high temperatures, over 1400 degrees Celsius. So free carbon, of course, is going to have an influence on the overall microstructure of the PDCs because it does exist within the PDC structure. And at one time, it was thought to be detrimental to almost all of the properties of PDCs. But more recently, it's been decided that PDCs with some high carbon content actually have very good resistance to crystallization and decomposition and some other kind of negative effects of the polymer to ceramic process. And so the existence of free carbon within the PDCs is going to again promote a more complex microstructure, which can block some of these negative effects like decomposition. And the next couple slides, I'm going to talk a little bit about some methods of kind of determining the structure and like where the free carbon is in these PDCs. So transmission electron microscopy is a tool that's used to characterize the morphology and the crystallinity and just kind of the structure of the material. And transition electron microscopy is going to be a localized surface characterization technique, so it can't really give information on the inner bonding or the energy of the molecules within the PDC. So it's going to be used for very small and thin specimens. So this is some examples of TEM imaging, and then over here, this is kind of the general layout of the instrumentation for TEM. So you're going to start with a light source, and then it's going to hit a condenser lens, which is going to focus a beam of electrons. It's going to hit the specimen, and then the objective lens is going to turn that resultant beam into a visible image. And then this intermediate lens and the projector lens here are going to magnify and project the image onto a screen so that the information can be obtained. And then again, these are examples of some imaging that can be gathered through this method. And then Raman spectroscopy is a very sensitive tool that's used to characterize a lot of different materials, but it's very, very useful for carbon. So Raman spectroscopy is based on the Raman effect, which compares and can analyze the energy levels of photons that are released by excited electrons. And the Raman effect was first discovered in 1928 by C.V. Raman. And again, that's going to characterize molecules by using their vibrational frequencies. So Raman spectroscopy can be used to perform both qualitative and quantitative analysis because it can identify which molecules are present, and it can also identify kind of how much is present in a sample. So this is kind of a general layout, sorry, the image is kind of blurry, of the instrumentation of a Raman spectrometer. So first you're going to have a laser source or a light source, and then it's going to split here. It's going to hit your sample to excite some of these specimens' electrons. And then the Raman effect kind of differentiates different scatterings of light. So then this filter here is going to collect the Raman scattered light, and then it's going to filter out all the other light, like the anti-Stokes light and the Rayleigh light. And then the light is going to be bent using this grater based on the wavelength, which is going to give kind of more of a range of it rather than a small beam. As you can see here, it comes into a bigger range. And then this detector is going to pass on all this information and turn it into kind of a spectra, which you can see more here. So this is what you're going to get from a Raman spectrometer. I have a hard time saying these words. And so there are different bands here which are going to help you characterize different like types and phases of the material. So the G band here is going to represent some structured carbon when you're looking at carbon, and then the D band is going to represent carbon with a lot less structure and organization. And as you can see, both of these bands are impacted by having materials pyrolyzed at different temperatures. So that is what I have for this. And then, so when we're talking about the effects of excess or free carbon on the properties of PDCs, it's important to note that there are going to be different effects for different types of ceramics. So the changes to a lot of the properties that I've listed here and on the next slide are going to be pretty general for a lot of different types of ceramics. So for mechanical properties, elastic modulus, hardness and creep resistance, elastic modulus is going to be decreased, hardness is decreased, creep resistance is going to be increased by the presence of free carbon, and grain growth is going to be hindered, and that's because if you remember on this slide here, this carbon is going to form kind of like a framework or a boundary around those silicon grains. So that's going to hinder the grain growth, and that can be a helpful property for certain applications. Thermal properties were pretty minimally reported from what I read as compared to mechanical properties, but thermal properties are going to vary even more than mechanical properties. So with different ceramics, free carbon is going to affect them in many different ways. For oxidation resistance, there are few to little negative effects by free carbon, because any additional oxidation that would be created by free carbon can be prevented depending on kind of the structure and how well that carbon is going to be embedded into the microstructure of the PDCs. Corrosion resistance is going to be an important factor as well, because it's going to help the application of PDCs in harsher environments, and it can actually be improved by free carbon, which again can form kind of a physical or chemical barrier to corrosion of the other phases of the PDC. And then lastly, the tribological properties, which kind of have to do with friction and wear on the surface, can be impacted by the presence of free carbon, because it's going to be, again, structured similarly to graphite, which is a very good lubricant. And then as for the functional properties are, again, very important to PDCs because they have a lot of electrical applications, such as acting as electrode materials for lithium-ion batteries. So free carbon is seen to be having a much higher electrical conductivity than a lot of the other phases in the polymer-derived ceramic, because, again, the carbon is arranged similarly to graphite, which is going to be a conductor because of the presence of valence electrons. So the free carbon can help increase the overall conductivity of your material. And PDCs are already desirable for use as electrode materials for lithium-ion batteries because of some of their favorable properties, like being lightweight and strong. And then free carbon is going to enhance this desire because, again, it's going to increase the electrical conductivity of the PDC, and it also provides really great hosting sites for lithium ions for the lithiation and delithiation during the cell's process. So as you can see in figure 10 here, there are some lithium ions that are going to be held by the silicon backbone and the other molecules found in there, but much more they are attracted to these carbon rings here, and so that's going to be a much greater hosting site for those. And then so the overall big applications of PDCs are, of course, going to be impacted by their properties, and a lot of these properties are, again, going to be impacted by the presence of free carbon. So for example, ceramic fibers are, again, one of the most successful examples of PDC applications, and free carbon is going to help with some of these properties because it can limit, again, the grain growth of silicon, which is going to increase the strength of the fibers. And then again, energy systems are also impacted by free carbon, such as the lithium-ion battery electrodes that we just talked about on the last slide. And then here's just kind of a different way of imaging that the carbon is preventing that grain growth between these silicon molecules here. And then finally, I just wanted to kind of go over a general overview of everything I've kind of taken from this and learned from this. So basically, free carbon is going to play a very important role in the microstructure. and the structural evolution of the PDCs, and it's going to be essential for certain properties and for certain applications. And also, again, the status of the free carbon can be kind of controlled by changing the molecular structure of your precursor or your method of heating. So one of the important things that people are trying to do is to find a balance of the amount of free carbon in your PDC, which you can control for the most part, because again, it's going to help some properties, but it's also going to hinder other properties. So finding a balance is going to be very important moving forward for improving the applications of polymer-derived ceramics. So that is what I have.